Okay, so I'm going to be talking about my project on COVID-19 death rates and death tolls. So the outbreak of the COVID-19 coronavirus has so far killed over 276,000 people and has infected a confirmed 4 million. This open-ended project was intended to explore death tolls and death rates and hopefully provide some insight as to what's going on. In terms of data variables being used, I had recovery data. So COVID-19 recovery data was in cumulative format and it came from Johns Hopkins University. I also had predictor data on density, urban population, 2020 population, hospital beds per 1,000 citizens, sex ratio overall and based on age, lung diseases, death rates overall and for both sexes, median age, 2018 GDP, crime index, position of the country, and smoking rate 2016 data for as many countries as possible. I also had testing data, again in cumulative format, and this was for as many countries as possible. I also had case and death data. This came from the European Center for Disease Prevention and Control, and it was in mu and total format. The logical variables defined were rich and crime. So rich was 1 if the country was above average in GDP per capita, 0 otherwise. And crime was 1 if the country was above the mean crime index overall, and 0 otherwise. All these data points were joined based on country and by date. 2 main data frames were created. One contained data solely on cases, recoveries, testing, and deaths, and the other one contained data, the predictor data. The predictor data frame was shorter in length because there was less predictor data available for all countries. So topic 1 of the project was related to exploring the distribution and the time series change of variables related to death rate from COVID-19 using probability distributions. And part 1 involved the question of whether we could model the time series data of new deaths worldwide as a binomial or Poisson distribution. And it was theorized that this was possible because each case can be considered like a Bernoulli random variable with some probability of surviving and dying. This probability was thought to be relatively constant, enough so that the model should see some success. However, both models were pretty weak. The best binomial found was defined as total deaths equals active cases times 0.17 times the probability x less than or equal to day, where x is a binomial random variable with k and probability death rate, where size k is defined as the active cases divided by 1,000 rounded to the nearest whole number, and day is day since 2020 January 22nd. And death rate is considered to be the mean overall total death rate that we had. And so the plot is shown below, and as you can see, it's pretty weak. There was a prediction of an initial wave of deaths, which of course was not seen, and it predicted more deaths than what really happened at this point here. Well, it predicted there would be a greater rate of increase in deaths at that point. Yeah. And yeah, so it's clearly over predicting in the first 90 days. The Poisson model did not fare much better with near identical results, and this is unsurprising as the binomial tends to the Poisson in the limit of large n given many samples, and provided that they are approximately independent. The best model for the Poisson was defined as total deaths equals active cases times 0.17 times p, x less than or equal to day, where x is the Poisson random variable with a value 16.68705. Yeah. And so it was therefore concluded that modeling cumulative deaths via probability distribution is unlikely to succeed. Potentially multivariable regression could have yielded better results and better models, and revealed more about what's going on and what affects the death tolls. And so part 2 of this topic was asking how the frequency of death rates distributed, how is the frequency of death rates distributed? And does it converge at a certain value, or does it vary wildly? And so looking at a plot, we saw a seemingly low variance with a high concentration of death rates at around 2% and a positive skew. This suggested that a gamma distribution would be a good fit, and therefore one was overlaid with a shape parameter 1.06 and rate parameter 21.99. And this looked like a decent fit, but a chi-squared test showed that this was wrong, because we received a p-value of about 1.65 times 10 to the negative 37, and it was therefore extremely improbable that we observe a test statistic this extreme from the relevant chi-square distribution. So under the current evidence, we strongly rejected the null hypothesis that death rates follow a gamma distribution, and therefore fail to model the distribution of death rates in this way. This isn't actually that surprising, because we can see blips around here between 0.25 and 0.5, and these imply a standard distribution like the gamma distribution won't be valid. So a heavy-tailed distribution was thought to be a good idea. And so as such, a Burr heavy-tailed distribution was fitted, and this was the density function. This, by the way, was a gamma density function that was overlaid. And this had shape parameter 2.01. That was the first shape parameter. Second shape parameter 1.35, and rate parameter 16.97. Here we go. Running the two-sample Kolmogorov-Smirnov test resulted in a p-value of 0.073, which meant we failed to reject the null hypothesis at the 0.05 level of significance that the sample came from the relevant distribution. Therefore, it was concluded that death rate counts can indeed be approximated by the Burr distribution. And so we move on to the second topic, which is exploring correlations and independences within COVID-19 data. And part one was asking whether there was significant difference in mean death rates between rich countries and poor countries, where rich is defined as being above mean GDP per capita and poor is below. And so a difference was found, which was about 0.00249, rich being larger in terms of death rates, surprisingly. And at first the t-test was carried out to check if this was significant. And the t-test returned a p-value of 0.07699, which seemingly led to the acceptance of the null hypothesis of no mean difference in death rates between rich and poor countries. But the t-test was fundamentally flawed, because t-tests assume normality. COVID-19 death rates do not follow a normal distribution. And this is shown by the plot here, where there's an overlaid normal distribution. And it's also shown in the Shapiro-Wilk normality test, where we received a p-value less than 2.2 times 10 to the negative 16, meaning that the null hypothesis of no significant difference with the normal distribution was rejected. As such, a permutation test was to be used to carry out the test. And this was done because permutation tests have no prior assumptions. And so what was found is that it is indeed significant, as can be seen by this plot here. From the p-value was determined there was about a 4.2% chance of discrepancy by chance. And so therefore the null hypothesis of no mean difference was rejected at the 0.05 level of significance. This led to the surprising conclusion that richer countries have higher COVID-19 death rates. It was theorized that this is probably because poorer countries have less testing and are therefore less able to determine who has died from COVID-19, and this has occurred to such a great extent that we observed this. And so part two of this topic was asking whether crime and high death rates are independent, and this was to be done with a chi-square test. So a new logical variable, HDR, was defined, being 1 for countries in the upper half of death rates and 0 for countries in the lower half. And so below here is a contingency table for those variables. Crime already been defined. And so the chi-square test returned a p-value so small that the computer rounded it to 0. And this meant that the null hypothesis of independence was strongly rejected. Crime and high death rates are, unsurprisingly, related, and crime itself being correlated with many other critical variables in a society, such as wealth and how obedient the population is. And this implies omitted variable biases at play. And all this also ultimately suggested that crime will be useful in modeling for topic 3. And part 3 of this topic was exploring correlations of all our variables. And this was done by a heat map. What we observed is that death rate isn't actually strongly correlated with much at all, with much of the other predictive variables. And perhaps this indicates that death rate is relatively constant, therefore hard to model. And it indicates challenges for topic 3. Interestingly, we don't see high degrees of similarity overall as well.
Topic 3 had the goal of modeling death rate and Deathtoll. And so the first part of topic 3 was modeling death rate via logistic regression. And the first model was a univariate logistic regression using recovery data on HDR to try and model high death rates. As can clearly be seen, it's not a great model, and this is also reflected in the low McFadden pseudo R-squared value of 0.078. And this therefore meant a different approach was needed to explain more of the variance in death rate, and hence multiple logistic regression. And for multiple logistic regression, 7 models were trained on 80% of data and tested on the other 20%. The best models were determined as that which had the lowest squared estimate of errors on testing data, death rate values. To reduce spread of outliers, GDP 2018, population 2020, total tests were logged. Recoveries, cases 2, and cases were square rooted, however, instead of being logged because they had 0 values in their data. In order to deal with multicollinearity, some variables were dropped in accordance with a variance inflation factor step by step, and this led to only the density, urban pop, hospital bed, sex 0, sex 25, sex 64, sex 65 plus, female.lung, median.age, crime.index, population.2020, smoking.2016, females.2018, cases, recoveries days, total tests, rich and crime variables being kept. The first model was a logistic regression of death rate onto all the available variables. The second model is a logistic regression of death rate onto the interaction terms of all the available variables to the second degree. The third model is a backward-forward stepwise regression on the first model with AIC criterion. The fourth model is a backward-forward stepwise regression model on the first model with BIC criteria. The fifth model is a Lasso model of death rate onto all available variables, and the sixth model is a ridge model of death rate onto all available variables. The seventh model was a neural net model with threshold 0.1 of death rate onto all the available variables. Comparison on the testing data revealed the fifth model, the linear Lasso, to be best with the lowest SSC, about 5 times 10 to the negative 6. Overall, this model had a relatively poor R-squared value of about 0.49. Its adjusted R-squared was close, however, at 0.47, indicating that the model did not overfit and strongly explains some of the variance. It should be noted that in diagnostics, the residuals via fitted values plot didn't look random for low fitted values and indicated some heteroscedasticity. Moreover, we received a p-value less than 2.2 times 10 to the negative 16 in the Shapiro-Wilk test for normality, meaning that we rejected the null hypothesis. No significant difference with the normal distribution, concluded that under the current evidence, the residuals do not follow a normal distribution. These violations of standard linear regression assumptions could have compromised the model. And so we moved on to the second part of topic 3, which was modeling new deaths via linear regression. For this, 9 models were trained on 80% of the data as before and tested on the other 20%. The best model was determined as that which had the lowest SSE on testing data as before. To reduce spread of outliers, GDP.2018, population 2020, total tests were logged again, and recoveries, cases 2 and cases were square rooted again. In order to deal with multicollinearity, some variables were dropped in accordance with their variance inflation factors again, and this meant we were left with only the density urban population, density urban hospital beds, sex 14, sex 25, 65 plus female, long median age, GDP 2018, crime index, smoking 2016, cases 2, total tests, and rich and crime variables to model with. The first model was a linear regression of new deaths onto all the available variables. The second model was a forward-backward stepwise regression on the first model with AIC criterion. The third model was a forward-backward stepwise regression model on the first model with BIC criterion. The fourth model was a linear regression model of new deaths onto the interaction terms of all the available variables to the second power. The fifth model was a forward-backward stepwise regression model on this model with AIC criterion. The sixth model was a forward-backward stepwise regression model on the fourth model of BIC criterion, and the seventh model was a lasso model of new deaths onto all the available variables. The eighth model was a ridge model of new deaths onto all the available variables, and the ninth model was a neural net with threshold 0.1 of death rate onto all the available variables. Comparison on the testing data revealed fifth and sixth models to be equally best, with the lowest SSD 9.5 free times 10 to the 0. So looking at the fifth model, we had a strong R squared of 0.91 and similarly strong adjusted R squared of 0.8996, indicating that the model didn't overfit and strongly explained much of the variance. It should be noted, however, that the diagnostic plots were not promising, with the fitted values versus residuals plot not looking random on the left-hand side, although it was well spaced as the fitted values increased, and indicated heteroscedicity with p-value less than 2.22 times 10 to the negative 16 on a non-constant variance test, and 0.8932 looked very poor on the Cook's distance plot. Again, these violations of the standard linear regression assumptions could have compromised the model. So as an overall comment, I hope this project shared some insight as to the distribution of COVID-19 death rates and total deaths, and led to some ideas of the root factors at play with the constructed models. Although death rate frequency was successfully modeled by a Burr distribution, probability distributions are not likely enough to successfully model and predict overall deaths. As such, regression models are likely the way to go forward for better modeling. The project concluded with a not so successful attempt at this with a logistic regression for death rates, but it also concluded with a really good new deaths model being developed. And this was in fact the best overall model from the project. For in future, the deaths model, in future, some things could be done. So the deaths model, the death models, and the other death rate models, well, we'll know more to how. The death models were plagued with diagnostic errors, implying that assumptions of standard linear regressions were being violated. It is possible to adjust the coefficients of one's model using the sandwich library, such that the assumptions of standard linear regression are met. This would clearly be something wise to do for greater application of any developed model. And it would also be good to do some n-fold validation to better assess predictive performance of any model overall. Moreover, it could be interesting to look at and evaluate each coefficient in models, in the regression models, and explain these from a biological or epidemiological perspective. And this could potentially help policymakers better deal with the current outbreak and potentially future ones. Furthermore, the current model could use more variables. For instance, a new dummy variable could be used to indicate whether quarantine restrictions are in place. This example in particular could help determine whether restrictions are effective. Indeed, this and more variables would likely let any model explain more variance in deaths or death rates. Finally, building a more in-depth interlinked model system would be advantageous. I perceived an idea of modeling first susceptible individuals, and from that infectious individuals, and from that recovered individuals.
This would be a freeway system that could cover the main principles of how a virus spreads and could potentially lead to more dynamic simulations and more accurate models. All right, well, that was my project. I hope you enjoyed the video. Thank you.